As you can see in front of me, I have a lot of batteries and I want to compare their life. These are zinc batteries, as you can see, called super heavy duty zinc. We'll see about that. I also have some alkaline batteries, extra life, and some name brand Simply Duracell alkaline batteries. I also wanted to test the performance of some voltage regulators. This is a 5-volt voltage regulator, so is this one. And I want to use one of them for one of my future projects, so I would like to compare their performance. In order to do that though, I need to build a circuit that draws a constant current and compare them to each other. And here's the PCB that I designed. I'm gonna do a build and we can test it and see how it performs, and then we can test the batteries and the voltage regulators using this. Okay, so let's start. Here is a picture of the schematic, and I'm gonna walk you through what each part does. And here are all the parts in a tray that I'll be using. Here's the schematic, as you can see. First things first, I'm using a 9-volt battery that's connected to a 5-volt voltage regulator. I use a low dropout linear regulator, and I'm disconnecting it using a switch just to save battery power when I'm not using the device. I'm missing a output capacitor and an input capacitor. The circuit might work fine without it, but the voltage regulators tend to be unstable without these capacitors, so I'm just gonna solder them on the PCB directly later. That's not gonna be an issue for me. And I'm using a resistor network to divide the 5-volt voltage by 2. I have a fixed 10K resistor and a 10K potentiometer. It's a 25 turn potentiometer to create the voltage reference. I wanted a fine adjustment. After that, we have the input terminal. That can be a power supply, can be a battery, whatever device that you want to test goes here. Then we have the op-amp that is powered from 5 volts and ground. You should use a rail-to-rail op-amp because otherwise you're not gonna get 0-volt output, which in turn means you're not gonna get 0 amps output or 0 milliamps. Depending on how low the op-amp can go, you're gonna get that output current. So it's not a good idea. The price difference is not that much, so just get a rail-to-rail op-amp. Otherwise you need to go with a much more complicated split supply. As you can see, I've just connected it to ground. The negative rail is connected to ground and the positive rail is connected to 5 volts. What an op-amp does is to basically look at the voltage reference that you put on the non-inverting terminal or the positive terminal and change the output to basically match the voltage on the non-inverting input as well. These two voltages should be the same on an op-amp, and the voltage on the non-inverting input is the voltage across these resistors. As you can see, these are 1 ohm power resistors, and the output of the op-amp is connected to two MOSFETs, N-channel MOSFETs. I use the IRLZ44N, and I use logic level MOSFETs because I'm only supplying it up to 5 volts and I want the MOSFETs to be able to fully turn on at 5 volts. What op-amp does here is basically change the gate voltage of these MOSFETs and drive them in their linear region, so the voltage drop across the resistor is equal to the voltage reference that you set, which, if you know Ohm's law, means voltage equals current times resistance. resistance is 1 ohms, so voltage is going to be equal to the current in each output. But here we have two outputs, so the current is going to be twice the voltage. And as you already know, we're dividing the voltage by 2, which is 2.5 volts. So we can get 2.5 amps per channel, which is 5 amps total. The resistors are also going to dissipate quite a bit of power, and they're going to heat up, and they're not very temperature stable. The resistance is going to change. So I suggest, instead of just reading this voltage reference and relying on the fact that the current is twice the voltage, actually use an external ammeter and check your output current. Also, let the device heat up and reach a thermal equilibrium before you proceed to your test, because that can create an error. If the resistors are cold and they heat up and they drop resistance, then you're gonna get higher amperage going through them and bad things happen. Just keep that in mind while you're making the circuit. The wattage of this circuit depends on the heat sinks that you use and the MOSFETs that you use, but I'm gonna limit it to 10 watts because I don't want anything to overheat. And let's start building the circuit. When doing assembly soldering, you need to use tweezers because the parts are way too small for you to hold by hand during soldering. So I will be using these two tweezers in order to help me perform the soldering. And I will also use lead solder because lead free is just too difficult to work with. I will also use some flux if I see the need. It helps the solder joint flow better. It's not necessary, you can get by without it. I will also use some solder wick to wick out any short circuits or any mistakes that I make. So without further ado, let's start soldering. Okay, now I've soldered up the voltage regulator, the output capacitor, and the input capacitor. As I said, I forgot to include them on the PCB layout, so I've just soldered them directly where they belong. Now I'm just gonna use some flux to clean up the joints a bit. That's way too much flux. Probably should stop watching Louis Rossmann. When you're using flux, you should have one of these fume extractors because it's gonna produce a lot of nasty fumes. You don't want to breathe that in. And here we go. Okay, that's all good. Now I'm just gonna use a bit of paper tissue to clean up the remaining flux. We have to clean it properly using alcohol next, but I'm just gonna do a bit of cleaning right now. Okay, there we go. Let's clean up. If you leave the flux on the PCB, it can create corrosion, just like water damage. It's not water damage, but it's gonna mess up your PCB. So always clean it using alcohol after. Even if you're using no clean flux, it's still a good idea to clean it anyways, because it's really gonna help you in the future. So next I'm gonna solder the power switch. It's basically gonna disconnect the battery when it's not in use to save your battery life. As you can see, it goes on the other side of the PCB like this. Okay, now we come to the other side, make sure it's sitting flush and solder it in. Okay, the power switch is also soldered now. let's move on to the battery holder. I will be using a 9-volt battery as the voltage source here. Just gonna place it like that. It's hard to see. There we go. Before we solder it though, I have some nuts and bolts. I've trimmed the bolts down to size, and I'm just gonna connect them to secure the battery holder on the PCB. The solder joints are not gonna be strong enough to hold it on their own. Again, it's hard to see this angle, but here we go. Just put in the nut. As you can see, it sits flush. I'm just gonna use a screwdriver to make sure it's sitting nice on the PCB and it's not gonna come off. That's one. And here goes the other one. Put on the nut. Secure it with a screwdriver. And there we go. Okay, I've soldered in the battery connector on the other side. I've trimmed the extra length of the pins using some side cutter or flush cutters. Now I'm gonna do the voltage divider section, which is this fixed 10K resistor and this 10K potentiometer. Okay, now we're gonna flip it, bend the pin so it stays. I'm gonna do it using the tweezers. This is not what they're meant for, but hey, it works good enough. It won't stay. Okay, so I have to solder this one while I'm holding it. Again, I'm gonna trim the extra length of the pins using some flush cutters. Don't cut them from the stem because you can damage the solder joint. Cut a bit higher, it's not gonna do anything. Just want to make sure you don't damage the solder joint or put stress on it, because then you'll have a lot of issues in the future. I also need to solder the pin on top because my holes are not plated. If you get a professionally made PCB, you don't need to do this, but in my case I have to. I'm also gonna solder the ground pin to have both the ground planes connected together. Here's the ground pin. I'm gonna solder it on top as well. Again, if you're using plated through holes, this is not gonna be an issue. There we go. Okay, let's solder in the op-amp now. I'm using a rail-to-rail op-amp because I want the voltage range to go as low as possible. The higher voltage, it's not really an issue. Make sure you orient the chip properly. And of course it's not gonna fit because I need to bend in the pins a bit. You can get some devices that squish the pins together and make them fit through the holes perfectly, but hey, I'm just gonna use my hands and fiddle around a bit. Okay, again, I don't have plated through holes, so I need to solder whatever is on top and on the bottom. Here we go, soldered on top. It seems to be good. Solder the ground connection. As I said, I want the ground planes to be as connected as possible, so I'll do my best to solder every ground connection on both sides. That's it. Now flip it to the other side. Okay, now let's do this connection here. That's really nice. Now we need to solder the rest of the connections on the other side of the board. Let's do that real quick. Okay, as you can see, I've shorted the solder joints here from the reference point to the ground. It's a really bad thing. You don't want to do that. So let's fix it using some solder wick. Grab the wick with the tweezers like that. It's also a good idea to add a bit of a flux, so let's do that. Let's add a bit of flux as well. Okay, grab it like that and remove the excess solder. Okay, I've cleared up the shorts off camera. And now we're gonna solder in the MOSFETs. But before we do that, we have to apply the heat sinks to them, because then it's gonna be much harder to do that, almost impossible after you have them soldered in. But before that, I've also noticed another issue. As you can see, when you put the MOSFETs through, it won't sit flush with the board and it just plays, and that's not good. So I'm just gonna use another nut or bolt or something to create a spacer so it doesn't rock back and forth, because that's gonna damage it over time. Give me a second. I found these M3 nuts which have the perfect spacing. They will touch the ground plane, but that's not going to be an issue, because on the MOSFETs themselves, they're just going to touch the plastic here and the plastic there. So I'm just going to use some super glue and glue them together. I'm going to do it off camera because I don't want to get everything messy. Okay, I've connected the heat sinks to the MOSFETs off camera, as you can see. Here's one, here's the other one. And now we're just gonna stick them in and solder them from the other side. I've also put the spacer in between, so it's gonna fit nicely on the board and it's not gonna wobble around. So bend the pins on the other side. Okay. Do the same for this one. Need to bend the pins a bit. I'm also going to use this helping hand to keep the heatsink in position when I'm doing the soldering, because it's quite heavy and it will flip like this one did if something is not holding on to it. So I'm just going to solder one of the pins here. Okay, that's good. Solder the other pin. And let's do the same thing for the other MOSFET. By the way, I forgot to mention, these are logic level MOSFETs. meaning they fully turn on at 5 volts because that's all the driving voltage that I have. You can use regular MOSFETs, but you can't get as good of a performance as with logic MOSFETs, so keep that in mind while you're doing this. Okay, now let's trim the rest of the pins. Yeah, maybe a bit more. No. Let's get this out of the way. Okay, that's all the pins gone. Okay, so that's all the pins gone. Just have the residue here. Okay. I also need to solder some of the pins on top, which can be a bit of an issue. I'm just gonna do it off camera real quick. Okay, we're almost done. I just need to put these power resistors, these are 1 ohm resistors, on these and like that, and also apply some more thermal paste. As you can see, the ground plane acts as a nice heat sink, helping to dissipate more power. Okay, so I went ahead and soldered the power resistors and the input connector, as you see, both sides. And just need to trim this. Sorry, I forgot. Just gonna do that quickly. Okay, and as you can see, I made a bit of a mess. So I've got the brush, some alcohol, some Q-tips, and some rubber feet to attach at the end. I'm just gonna clean up the mess, especially the flux residue. You do not want to leave that on the PCB. So I'm just gonna go with the brush over the entire board. Get every single component best I can. I'm gonna fast forward until I'm done with this side. Okay, now I'm just gonna use these Q-tips to get the thermal paste off on this area. Get as much as I can and clean up with the dry end. Make sure everything's cleaned up. Here's the other one. I think I used a bit too much thermal paste. That's okay, it's not gonna hurt anything. It's just gonna keep the temperatures down. So if anything, that's a good thing. Now I'm just gonna go over with the brush again. Clean everything the best I can. I know it's a bit messy. Again, I'm just gonna fast forward to when I'm done. So I've also cleaned up the board. We're just gonna put some rubber feet on the back. Take one from here. Stick it in this corner. Take another one. Stick it over here. One more. And finally the last one over here. And I'm just gonna put a battery in it and test to see if it works or not. Here's the battery. put it in like so. Oh, and I forgot to mention I used some super glue under the potentiometer so it doesn't come off the board. And that's pretty much it. Now let's just see if we're getting the 5 volts that we're expecting. I'm just gonna check quickly with a multimeter. After turning on the device and trying to test it, I noticed that after 5 or 6 turns of the potentiometer, the current would rapidly jump up to about 1 amp, and this MOSFET would get really hot, this one would remain cold, and I tried measuring the resistors using the multimeter, but it's a cheap multimeter. I didn't have any luck. It was reading about 2.1 ohm on this resistor and 1.5 or 1.6 in this one. And I already know that these are 1 ohm resistors. They are 5% tolerance, so that measurement was completely out of the water. And I couldn't see any shorts by myself. I tried inspecting it really quickly, but I didn't see much. So I left the device on for a bit, and this MOSFET was burning hot. This one was still stone cold, and these resistors were both warm. One of the possibilities was that this MOSFET was blown or it wasn't soldered on properly, but that would also mean that there is no current flowing through this resistor either, because this is the shunt resistor for this MOSFET. So that resistor shouldn't be getting hot at all. And the fact that it was touchy told me that there should be a short circuit somewhere, but as I said before, I couldn't see it visually. The fact that these were both getting hot told me that there should be a short across one of the resistors, and given that this MOSFET was remaining cold, I checked the connections of that resistor using a magnifying glass, and I'm gonna show you a picture. There is a really smart short to the ground on this resistor on the other side over here, which I fixed, and the board works fine now. So let's hook it up and have a look as how it performs under test. As you can see here, I have an Arduino microcontroller, I have my load, I have a 12 volt supply, and this is a INA 219 current sense amplifier that is connected to the Arduino, and I'm reading the data on the computer. Here's the data on the computer. As you can see, I have 12.5 volts supply. That's gonna drop to 12 volts as I increase the load. I have 0 milliamps input because the load is off. This is just a noise signal. Don't worry about it too much. And the power should also be 0 milliwatts. Again, that's just noise. So let's go ahead and turn on the load and put some load on and see how the circuit behaves. So I'm gonna turn it on, and as you can see there's an instant jump. I have it all the way set to 0, but as I said, even the rail-to-rail op-amps have a bit of an offset, so that's the offset current that you get. So now let's increase the current slowly. And there we go. Now the potentiometer is working. We have about 30 milliamps. Let's increase it a bit more. As you can see, I have quite a fine adjustment. 45 milliamps. Let's go higher. And I'm gonna take it all the way up to 1 amp now. Okay, 300. 400, 500. As you can see, it is working quite well. I can feel the MOSFET starting to get a bit warm. Okay, we're at about 1 amp. Yeah, there we go, 1 amp. And as you can see over here, the voltage started to drop as we increased the current. Now that's a flat 12 volts as well. The reason that you don't see it go beyond 1 amp much more here is because I have the INA 219 and the 1 amp range. That's much more accurate for reading lower currents, but as I said, this load can go up to 5 amps. So there we are. Next thing is to test out the batteries using an automated test method. I might make a video explaining on how to do that later, but that has to be a later video. For now, this circuit works fine, and as you can see, the light has gotten a lot dimmer. It's practically off right now, and that is exactly why I want to test the batteries to see which one lasts longer, which one provides more capacity per dollar, and things like that. That's it for today. Catch you guys later. Bye.